Hey guys, in this video I'm going to cover all the reactions in AS Organic, hopefully under 30 minutes. Let's start with the reactions involving alkanes. On alkanes, there are three reactions you need to know: combustion, cracking, and free radical substitution. So combustion is when you take a hydrocarbon, say CXHY, right, and you react it with oxygen. You react this with oxygen, and what you get is CO2 plus water. Now, this X and Y, this X is the number of carbon atoms and Y is the number of hydrogen atoms. Now, there is a general formula you can use to solve these types of questions. So, CXHY and X plus Y by 4, and then there is an X next to this CO2 plus Y by 2. You can use this formula to balance this equation. And they'll usually give you the number of carbon atoms and the number of hydrogen atoms, and you'd have to balance this type of equations. Then comes cracking. Cracking is when you take a hydrocarbon, let's say C4H10, and you break it, you crack it, and you make two smaller hydrocarbons. Now, these two smaller hydrocarbons can be any combination, or so that the combination adds up to 4 carbons and 10 hydrogen. So you could make C2H4 plus C2H6. This is an alkene, this is an alkane. Now, the next reaction is free radical substitution. In free radical substitution, there are 3 stages: initiation, propagation, and termination. Initiation is when the chlorine, or it's usually chlorine or bromine. Now, this Cl2 or Br2 has this bond. And when you give enough UV light to this, right, this bond would break. And when it breaks, it produces 2 free radicals. Each will gain 1 electron. Now, these two atoms are known as free radicals. This is initiation. This reaction where you produce 2 free radicals is known as homolytic fission. The next step is propagation. Now, propagation is when you take the alkanes, let's say CH4, and you react it with a free radical, let's say chlorine free radical, and what you get is a free radical plus HCl. And this propagation reaction will continue until you have a free radical. Now, termination is when 2 free radicals, it can be any free radicals, let's say this and this reacts together and they produce a molecule. What do I mean? Well, CH3 free radical will react with a chlorine free radical to make CH3Cl. Since there is no free radical being produced, this reaction can not continue anymore. So termination is when propagation ends. These were all the reactions you need to know for alkanes. Now comes the alkenes reactions. In alkenes, the first reaction is addition reactions. And whenever you need to know the mechanism, I would write mechanism on top of that reaction. So addition reaction is when you react an alkene with HBr. And what you get is an alkane. The only reagents you need for this is HBr. And the condition is room temperature. This double bond is sp2 hybridized. And the pi bond in the double bond breaks and becomes sp3 hybridized. Now, you need to know the mechanism for addition reaction of the alkene with HBr. So H is positively charged, bromine is negatively charged. This has 2 electrons between the bond. Now, as HBr approaches this double bond, which is highly electronegative, which is highly negative, the electrons get repelled to this bromine. So this bromine takes both of the electrons. Now, although bromine has this negative charge, the highly negatively charged double bond forces these electrons towards bromine. Bromine takes both of these electrons. What happens? Well, this hydrogen right here, which is positively charged, gets attracted by this double bond right here. So the double bond attracts this positively charged hydrogen, and the hydrogen forms a bond with the carbon atom. It can be any of these 2 carbon atoms. Now, I have this plus a bromine which is negatively charged. This carbon right here has 1 missing bond. You can fill this bond up, right? And this carbon is positively charged because it needs an electron. Now, this bromine will attack this carbocation and form this final compound. So one carbon gets the hydrogen, the other carbon gets the bromine. Now, this form is known as the intermediate. Intermediates have carbocations. Step 1 is these 2 electrons are taken by this bromine. So you draw a curly arrow towards bromine. Step 2 is this double bond attacks the positively charged hydrogen. So you draw a curly arrow towards hydrogen. Step 3 is bromine attacks the carbocation because the carbocation has a positive charge. You form this bromine carbon bond and you get this compound right here. Then comes hydrogenation and dehydrogenation. Hydrogenation is when alkenes reacts with steam to form alcohol. The reagent for this is obviously steam, and you also need a catalyst. This catalyst is H3PO4 acid. It can be dilute or conc, and the conditions are high temperature and high pressure. The next reaction with alkenes is the mild oxidation of alkenes. Now alkenes will react with cold dilute KMnO4, and what you get is a diol. So so the double bond breaks and you get OH on both of the carbon atoms. Now both of the carbon atoms that was with the double bond. The reagent for this mild oxidation is cold dilute acidified KMnO4. Write this complete sentence. And remember, it should be cold, so that means the condition is room temperature. And there's also an observation because KMnO4 is colored. So the purple solution will decolorize when the alkene oxidizes. So here are some examples of mild oxidation. So let's say I have CH2 double bonded to a CH2. When mild oxidation happens, you need KMnO4, dilute, cold, acidified. And what you get is this CH2, right? There is two hydrogens, and then the double bond, which was originally this, right, would break into a single bond, and both of the carbons would get alcohol group on them. So yeah, this like this, and then this carbon also gets an alcohol group. The next reaction, where I have a CH3 on a carbon with a hydrogen, I have a CH3 with carbon and a hydrogen double bonded to a CH2. Now when this reacts with the cold dilute acidified KMnO4, I get CH3, carbon, hydrogen, and then the double bond was here, but now the double bond would break. I will get OH on the carbon which had the double bond, and then this carbon will also get a double bond this carbon will also get an alcohol group with a hydrogen and a hydrogen like this. There is also another hydrogenation reaction where an alkene reacts with hydrogens to form an alkane, and the double bond would be gone now, and you get two hydrogens with the carbons that had the double bond. So two hydrogens on either side. Now the reagents for this reaction is obviously hydrogen gas, and you also need nickel catalyst. The conditions for this reaction is only heat. Now the last reaction involving alkenes is elimination. Elimination is when you have an alcohol which would undergo dehydrogenation. Dehydrogenation is when you remove a water molecule, and when you do that, you get alkenes. This OH on this carbon atom plus a hydrogen on another carbon atom, so let's say this hydrogen right here, would be removed, and what you get is this carbon, two carbons with double bonds, and these two hydrogens would still remain right here. So you remove an OH and a hydrogen from the two carbons and you get an alkene. The reagent for this is only conc H2SO4, and condition is only heat. Now earlier I talked about mild oxidation of alkenes, where an alkene underwent mild oxidation which involved cold KMnO4, and what we got was this double bond would break and we would get a diol on both carbons that had the double bond. But now comes the more interesting part, known as strong oxidation of alkenes. Now in strong oxidation of alkenes, things get quite complicated. So an alkene would undergo strong oxidation to produce either an aldehyde, or a ketone or an acid, these three things. Now what is an aldehyde? Simply said, aldehyde is a carbon atom that has a double bond O with an H, and we don't care what's present here. It can be an R group meaning CH3, CH3, CH2, or literally anything that has a carbon. Now a ketone is C with a double bond O and R groups on either side. Now these R groups are simply carbon which contains some other group that we don't care about. And acid obviously is C double bonded to an O and then an OH, right? So now that we know what these three things are, an alkene undergoing strong oxidation of alkenes would either produce an aldehyde or a ketone or an acid. And what are the conditions? Well, in mild oxidation of alkenes, I used KMnO4, right? And it was cold. But now this KMnO4 is hot. and also it is acidified. H plus simply means it's acidified. So I have this compound right here, and you can see a double bond, which means this is an alkene. If this was mild oxidation, then the double bond would break, right? And what I would get is OH on either side, so a diol. But in strong oxidation, right, I would produce two of these things. One aldehyde, one ketone, one aldehyde, one acid, one ketone, one acid. It can be any combination, depends on the compound. So I have this double bond right here. It undergoes strong oxidation with KMNO4, hot and acidified. And when it does this, the double bond breaks. The double bond would break, and this compound would split, as well as this compound would split. So I would get two different compounds. When that happens, right, I would get CH3, and on the other side of this compound, the right side, would be C with a CH3 and a CH3. Now, so I need to make two more bonds right here. I need to make two bonds. But when it splits, I would get double bond O at the place where the split happened. So the split happened here. So this carbon right here would get a double bond O, and this carbon would get C double bond O as well. Now, when that happens, I would get this molecule and this molecule right here. Now, it gets even more interesting because this compound on my left is an aldehyde because it has a C double bond O and an H. This is a ketone because it has two R groups, right? And a double bond O with a carbon. So this right here is a ketone. Now, what's even more interesting is that in strong oxidation of alkenes, whenever you produce an aldehyde, because this aldehyde has one extra hydrogen, this gets oxidized as well. So this hydrogen gets oxidized and it gets an O. Earlier I had an aldehyde. Because of this KMNO4 and it's hot and it's acidified, the conditions are so strong that the hydrogen which was on the carbon with the double bond O gets oxidized and becomes carboxylic acid. So aldehydes under strong oxidation would become an acid group. Aldehydes would become acid, but ketones doesn't have an extra H. It simply has an R group. It simply has two R groups with double bond O, and I don't care what is on the double bond. And I don't care what is present on these R groups. I don't care how many hydrogens are present on the R groups. I simply care about the carbon which is bonded to the double bond O. And if this carbon has an H when it undergoes strong oxidation, then this hydrogen would get an O to become acid. But this won't happen in ketones because ketones only has two R groups. So there is another rule that you need to know in strong oxidation of alkenes. When you have a carbon which is bonded to two hydrogens, right? Two hydrogens and double bonded to another carbon, meaning it has a double bond, and it undergoes strong oxidation, this double bond would split, this would break, and you'd get two different compounds. Now, the right side would be C with a CH3 and a CH3, and you'd get a double bond O, right? And this is ketone because it has two R groups. Now, what would this become? This would simply become CO2. It's just a rule. You don't need to know why this happens. You only need to know that whenever this carbon has two hydrogens, you'd get a CO2. And now, let's say I have this compound and I've been told that it undergoes strong oxidation. When this undergoes strong oxidation, remember the conditions are KMNO4 and it should be hot and acidified. Instead of hot, you can also say heat. And when this happens, when it undergoes strong oxidation, the double bond would split. The double bond splits and you get two different compounds. Now, I have a CH2 that has a double bond. So one product is CO2. The right side is CO2. What is the left side? The left side would simply be CH3, CH2 with a carbon that has a CH3, and this double bond would break and I'd get an O right here. Now, will this further oxidize to become an aldehyde? Now, will this oxidize further to become a carboxylic acid? No, because this is a ketone. And ketones don't have an extra H on the carbon double bond O. Now comes polymerization. Polymerization is, I think, also part of alkenes because polymerization, for polymerization to happen, you must have a monomer, and monomers must contain C double bond C. So I have this compound right here. When it undergoes polymerization, I get a polymer that has carbon. The double bond would break. In the polymer, the double bond breaks. I get hydrogen, chlorine, and hydrogen. And I would extend these two double bonds because what would come right here is this continuation of this monomer without the double bond. There would only be single bond present. I'll explain this in a moment. But when you draw polymer, right, you get this this thing right here. You would break the double bond, you would extend the bonds, carbon bonds, and you would draw two lines with an N. And this N represents the number of polymers. That was the end of alkenes. And honestly, from here on, things get fairly easy. So, starting off with halogenalkanes now. Some properties of halogenalkanes are that they are colorless liquids, they are insoluble in water, and there are three types of halogenalkanes: chloroalkanes, bromoalkanes, and iodoalkanes. So, we know that down the group, meaning chlorine, bromine, and iodine, right, the number of electrons increases rapidly. So, since number of electron increases, the melting point would also increase down the group. So, down the group, the melting point of halogenoalkanes increases. Now, there are three types of different halogenoalkanes that you need to know. So, first of all, what I have right here is a carbon bonded to two hydrogens, and X is a halogenoalkane. It can be chlorine, bromine, or iodine, doesn't really matter. But the point I'm trying to make is that I have one R group attached to this carbon atom, which also has a halogen attached. So, when this carbon has one R group, it is said to be a primary halogenoalkane. Now, let's say I keep this R group where it was, and I removed one hydrogen and added another R group. Now, this carbon which is attached to this halogenoalkane has two R groups. When it has two R groups, it is said to be a secondary halogenoalkane. Similarly, when I remove this hydrogen right here and I attach an R group to this carbon which has a halogenoalkane, since it has three R groups, it is said to be it is said to be a tertiary halogenoalkane. So, nucleophilic substitution is when any of these four nucleophiles, right, OH minus, H2O, NH3, or cyanide ion, would react with halogenoalkanes. So, any nucleophile plus a halogenoalkane would result in the formation of an alkane that has the nucleophile, and this halogen gets replaced by this nucleophile, so you get the halogen as well. Let me just write X. The nucleophilic substitution of OH minus ion can also be said to be hydrolysis. Any halogenoalkane would react with this OH minus that has a lone pair, and you'd get ROH plus the halogen ion. So the reagents for this is NaOH aqueous, or you can use potassium hydroxide, right, which is KOH, and the conditions are you heat under reflux. Let me give you an example. Let's say I have this halogenoalkane because this carbon has a bromine, so this is a halogenoalkane which reacts with a nucleophile, in this case OH minus ion, and you use aqueous NaOH and heat under reflux. So, and what you get is the same compound. Literally everything is the same, but the place where the bromine was initially gets replaced by the nucleophile, which is this right here. And be careful, this nucleophile, this carbon is bonded to the O, not the H. Alright, so the nucleophile gets replaced, and what you get is this bromine ion, because bromine was the halogen in this case. Now, in the exam, they expect you to know the mechanism for nucleophilic substitution reaction. So, any four of these nucleophiles would attack this carbon with the halogenoalkane. So, I write nucleophile, right, with a lone pair, which is negative. This would attack the partially positive carbon atom. First thing is you write the partial positive and negative charges. Carbon is partially positive. Bromine, since it's electronegative, it's partially negative. And then you draw the curly arrows. Now, since this is partially positive, the nucleophile would attack this carbon. So you draw a curly arrow towards the carbon. You also need to draw the lone pair and the negative charge on the nucleophile. And what you get is this nucleophile being attached to the carbon atom plus the bromine, which has one lone pair. Now comes the substitution with the cyanide nucleophile. Now this is also known as nitrile reaction. Again, any halogenoalkane would react with a cyanide ion to give you RCN plus the halogen ion. And nitrile reactions are the only reactions in which you increase the carbon chain by one carbon atom. Now, the reagent for this reaction is KCN, potassium cyanide, or you can use NaCN. And either of these, must be dissolved in ethanol. The conditions for this reaction is you heat under reflux in ethanoic solution. Now, I have a halogenoalkane which would react with a cyanide ion. The bromine would get replaced by this cyanide ion, and you would also get a bromine. So you can see that instead of drawing nitrogen as CN, I can remove this and draw the nitrogen bond like this. CN nitrogen bond is like this. And you can see that there are 3 carbon atoms in the chain. Initially there were 2, now there are 3. So a good way to figure out if this is a nitrile reaction is that the carbon chain increases by 1 carbon atom. So earlier I told you how nitriles are formed. Now nitriles under certain conditions can hydrolyze to form a carboxylic acid. So let's say I have CH3, CH2 and CN. Now this CN makes this compound a nitrile. So nitriles under certain conditions would hydrolyze to get you CH3, CH2, the same compound, the same R chain right here, but this CN becomes CO2H now. Now hydrolysis, remember, can only occur when you have water, right? So the reagent for this reaction is HCl, and it should be dilute. Why it should be dilute? Because again, you need water as well to hydrolyze. So dilute HCl, and the condition is that you heat under reflux. Let's say that I have this compound right here which has 2 halogens at the terminals, and I want to add cyanide ions at the terminals. So it's the nucleophilic substitution with the Cn minus ion, right? So I react this with NaCN dissolved in ethanol, and you heat under reflux in ethanolic conditions, and what you get is cyanide at either ends. And let's say that this compound undergoes hydrolysis. What are the conditions? Dilute HCl and heat under reflux. So what you get is CO2H, CH2, CH2 and CO2H. The cyanides get replaced by carboxylic acid group. Now the nucleophilic substitution doesn't end. Now ammonia, which is a nucleophile, also reacts with halogenoalkanes and nucleophilic substitution happens. So the first nucleophile was OH ion, then came the cyanide ion, and now comes the NH3 ion or ammonia. So a halogenoalkane and Rx, where X is a halogen, would react with ammonia under certain conditions to give you an R NH2 plus an H bonded to the halogen, so HX. Now what are the reagents and conditions? Well, you obviously need ammonia, and it should be concentrated, and it should also be dissolved in ethanol. And the conditions are you heat under reflux. let's say I have this compound and I react this with ammonia, which is concentrated and it's dissolved in ethanol, and you heat under reflux, and what you get is the same R group, right, CH3, CH2, but the Br gets replaced by the NH2. Now there is one extra hydrogen left, and that hydrogen would bond with this Br right here. Now this Br will bond with the extra hydrogen to get HBr. Now there is one last reaction involving halogenalkanes that you need to know, and it's different because the earlier reactions I told you about were all nucleophilic substitution and one hydrolysis. This one is elimination. And why is it elimination? Because a halogenoalkane under certain conditions would become an alkene. And what would get eliminated is the halogen and a hydrogen. So one halogen and one hydrogen would get removed, and you will get this double bond. The hydrogen which would get removed would be from the carbon which is adjacent to the carbon that is bearing the bromine or the halogen. The reagent for this is very similar to the nucleophilic substitution with the OH ion. So the reagent are NaOH, and the condition is heat under reflux. But wait, this NaOH in the case of nucleophilic substitution with the OH ion was aqueous, right? But in this case, in the case of elimination, this NaOH would be dissolved in ethanol. Now comes the reactions with alcohols. So some facts that you need to know about alcohols is that they are very soluble with water. The reason being is that alcohols have the OH group, and OH is hydrogen bonding. So they form hydrogen alcohols, or OH group forms hydrogen bonding with water, and therefore they are very soluble. But this solubility decreases as the R chain increases. The reason being is that the R chain, which is carbon, basically carbon atoms, are non-polar. So if I had methanol, ethanol and propanol, methanol would be the most soluble and propanol would be the least soluble in this case. So the first reaction involving alcohols is with sodium, and it's very simple. So basically any alcohol would react with sodium atom to give you this ion, where the H of the alcohol would get replaced by the sodium. And there are no conditions for this reaction, you just need sodium. And remember that one OH functional group gives you half a mole of hydrogen. And you need to know the observation of this reaction. Since hydrogen is a gas, there would be fizzing, and a lightened splint would give a pop sound when placed in hydrogen gas. So that's another observation. So the next reaction involving alcohols is the conversion of alcohols to halogenoalkanes, and there are different reagents and conditions for the formation of chloroalkanes and the formation of bromo and iodoalkanes. So let's start with the formation of chloroalkanes. Now any alcohol under certain reagents and conditions would form a halogenoalkane where the OH gets replaced by the halogen. In this case it's chlorine, so the OH gets replaced by chlorine. The reagent for this is PCl5, and the condition is room temperature, and this PCl5 should be in liquid state. One of the 5 chlorines gets replaced by the OH alcohol group, so I'm left with 4 chlorines now, and this hydrogen, right, would combine with one chlorine from this PCl5 and form HCl. Now I'm left with 3 chlorine atoms, so the rest of the reagent would form POCl3. HCl gas is white fumes. So this is a test for alcohols, remember that. So now comes the formation of bromo or iodoalkanes. The reagents and conditions are very similar, so I combined them both. Now the reagent that you need for the formation of bromoalkanes is conc HBr, and the condition is heat under reflux. So, and the reagent for the formation of iodoalkane is conc HI, and the condition is still the same, heat under reflux. Now there is also an alternative way of forming bromo or iodoalkanes, which is not very popular, but it's better if you know this. So red phosphorus plus bromine or iodine, and you add the phosphorus separately to the bromine or iodine. So alcohol would form bromoalkane if you have conc HBr and you heat it under reflux, or you add red phosphorus with bromine. And Iodoalkanes would be formed from alcohols if you add conc HI and heat under reflux, or you add red phosphorus to iodine. So now we move on to alcohol oxidation. So alcohols, like alkenes, can also get oxidized. And alkenes use one of the oxidizing agents which I'm going to talk about. It's KMNO4. I'm sure you've seen this oxidizing agent earlier. But there's another oxidizing agent we can use, and that's K2CR2O7. Now, what's the difference between these two? KMNO4 is a much stronger oxidizing agent compared to K2CR2O7. So this oxidizing agent is relatively more stronger. So primary alcohol is an alcohol that has only one R group. Secondary alcohols have two R groups attached to the carbon, which has the OH group. And obviously tertiary has three R groups. Now primary alcohols can oxidize to form aldehydes. Secondary alcohols can oxidize to form ketones. And tertiary alcohols do not oxidize at all. So there is no oxidation. Now why do alcohols form different products when they are oxidized? Well, because of the hydrogen atoms. The H from the alcohol group is removed, as well as the H from another atom which is bonded to the carbon. And in doing so, I get an aldehyde. So this hydrogen got removed, as well as another hydrogen from the alcohol group, and what I get is an aldehyde. Now, for ketones, why is ketones formed instead of aldehydes? Well, because when I remove one hydrogen from the alcohol group and another hydrogen from the carbon bonded to that hydrogen, which also has the alcohol group, in this case this hydrogen, what I get is carbon, which has the double bond O and R groups on the adjacent side, and this is a ketone. And tertiary alcohols do not oxidize at all because they don't have any hydrogen atoms to spare. Yes, I can remove this hydrogen, but I need another hydrogen to be removed from the same carbon bearing the alcohol group. And since I don't have any hydrogens to spare, therefore no oxidation occurs. Now, as I told you earlier, aldehydes have a special feature, which is that since they have one extra hydrogen, they can oxidize further to make carboxylic acid. So the aldehyde stays where it is, but the hydrogen gets oxidized into OH. So I get a CO2H group or a carboxylic acid group. Now, what are the reagents for oxidizing primary, secondary, and tertiary alcohols? You can either use KMNO4 or you can use K2CR2O7. And the condition is that you heat under reflux. And if I wanted to make a carboxylic acid from a primary alcohol, I would also use KMNO4 and heat under reflux. But now I only want to make aldehydes. So how do I do that? Well, I told you earlier that K2CR2O7 is a weaker oxidizing agent compared to KMNO4. So I use that. And I do not heat under reflux. What I do instead is I heat my primary alcohol and I distill off the product. Now let's say I have this compound right here which has three alcohol groups, and I use the standard conditions and reagents and I oxidize this entire compound. So first I need to identify the type of alcohols I have. Now this alcohol right here is attached to the carbon atom which has two hydrogens and one R group. So this alcohol is primary. Primary is 1. Now this alcohol right here is bonded to only one hydrogen and two R groups. So this alcohol is secondary. And finally this alcohol is bonded to three R groups. So it will be a tertiary alcohol. The only part that oxidizes are the alcohols. So first of all, this alcohol is tertiary, so it won't oxidize because tertiary alcohols do not have any hydrogens to spare. So I draw the tertiary alcohol as it is. Then comes the secondary alcohol. Secondary alcohol has one hydrogen to spare. So this hydrogen and this hydrogen gets removed, and what I get is the carbon, which is double bonded to an O, and then comes the next alcohol. This alcohol is primary. So this primary alcohol will oxidize to aldehydes. But wait, I have a strong oxidizing agent. and I'm using heat under reflux as the condition. So the aldehyde produced, which is carbon, which is double bonded to an O, and then a hydrogen. So what happened was one hydrogen got removed and another hydrogen got removed from the alcohol group. But this doesn't stop here. This will further oxidize because of stronger oxidizing agent and heat under reflux, and I get a carboxylic acid. Now what if I use the relatively less powerful oxidizing agent, the K2Cr2O7, and instead of heating under reflux, I heat the product and distill it? Nothing will change with the tertiary alcohol and the secondary alcohol. They oxidize as it is because K2Cr2O7 is an oxidizing agent. But with primary alcohols, instead of making carboxylic acid, I will now make an aldehyde. Now, I know that I can convert primary alcohols to aldehydes and secondary alcohols to ketones, but for both these reactions, there is a reversible reaction as well. So in simple words, aldehydes can be converted to primary alcohols, ketones can be converted into secondary alcohols. Now, what are the reducing agents I can use? Reducing agents that I can use. There are three reducing agents. The first one, which is the most popular, is lithium aluminum hydride in dry ether. This is the first reagent. The second reagent that I can use is NaBH4, which is aqueous. And finally, the third reducing agent is hydrogen and nickel catalyst. Now, this is popular also in alkene reactions, and I'll explain why that is important. But these are the three reducing agents I can use. And the condition for both of the first two reactions is I heat under reflux. And for the hydrogen and nickel catalyst, I simply use both of these. There is no condition. Now, let's say I have this compound right here, and this compound has an aldehyde group, and the examiner says that there are two reactions. I use two reagents for this reaction. One is hydrogen and nickel catalyst, and the second reaction is I use NaBH4 and I heat under reflux. So first of all, I have an aldehyde and I have reducing agents. So when I have a reducing agent, the reducing agent will reduce the aldehyde to a primary alcohol, and if in case of ketones, convert it into secondary alcohols. Now, will the double bond react with this reducing agent? No, because I didn't say there is any reaction involving NaBH4 and double bond, so I write the double bond as it is, and then I write CH, and then this carbon will gain two hydrogens, so addition of two hydrogens, right? And the C, which is double bonded to O, has one hydrogen already, but it will gain one more hydrogen from the reducing agent, and one more hydrogen would be gained by this O right here. So this O gains one hydrogen, the double bond breaks, and you get a primary alcohol. Now, I know that nickel catalyst and hydrogen reacts with this double bond right here. And when it does, the double bond would break. This carbon gains two hydrogens, so CH2, and this carbon also gets two hydrogens, so CH2 right here. And everything else would be the same. The double bond O will break and you'll get the OH, the primary alcohol, as it is. Now we move on to carbonyls. Carbonyls are basically aldehyde. Now we move on to carbonyls. Carbonyls are aldehydes, ketones, and carboxylic acids, basically anything with a C double bond O. So I told you earlier about alcohols getting oxidized to aldehydes and ketones. Primary alcohols, which has one R group, can be oxidized to aldehydes, where aldehyde is C double bond O, H, and an R group. Whereas secondary alcohols, which has two R groups, can be oxidized to ketones, where ketones is C double bond O with two R groups. And the reagents for this reaction is K2Cr2O7, or we can use KMnO4. And both of these should be acidified. Now, although there are two oxidizing agents which can be used, in total you need to know 4 oxidizing agents and the color changes that happen when you use these oxidizing agents. So the first one is obviously acidified K2Cr2O7, and you heat under reflux. And the color change that you get from K2Cr2O7 is orange initially to green. Now the second reagent is the more popular one, KMnO4, which is also acidified, and you also heat under reflux to oxidize these aldehydes and ketones. And the color change that you'll see is initially purple and then colorless. The third reagent is tolerance reagent, and you simply heat it, and the color change that you'll see is silver PPT, because tolerance reagent has Ag plus ions. And the final reagent that you need to know is something called Felling's solution, which has Cu2 plus ions. The color change that you will get is brick red PPT. And remember that Tollens reagent and Felling's solution are mild oxidizing agents. Now, there is a test for ketones and aldehydes, and the reagent that we use for that test is 2,4-DNPH. Now, simply that condensation reaction states that any aldehyde or ketone will react with 2,4-DNPH to give you an orange PPT. Now, let's say I have three compounds, A, B, and C, and I react each compound with two different reagents. So, suppose I have compound A, and I first reacted with 2,4-DNPH, and then I reacted separately with acidified KMnO4. And they tell me that, hey, it reacts with 2,4-DNPH, but compound A does not react with KMnO4. So, what is compound A? And they give me three options: aldehydes, ketones, or carboxylic acids. And immediately when I see something reacting with 2,4-DNPH, it can only mean that this compound is either an aldehyde or it is a ketone. And since my compound A does not oxidize any further, I can say that compound A is ketone, because if it was aldehyde, acidified KMnO4 would oxidize aldehyde to acids. But they tell me that it does not oxidize, so therefore compound A is ketone. Now compound B, they tell me that tolerance reagent would not react with compound B, but it would react with 2,4-DNPH. And I know 2,4-DNPH would mean ketone or aldehyde. And again, tolerance reagent is a weak oxidizing agent. So if it was an aldehyde, tolerance reagent would oxidize aldehyde to acids. But since it did not oxidize compound B, then therefore compound B is a ketone. So for compound C, they tell me it reacted with 2,4-DNPH, and it also reacted with K2Cr2O7, acidified K2Cr2O7. I know if 2,4-DNPH reacts with compound C, then it can only mean ketone and aldehyde. And since it oxidized compound C, and aldehydes get oxidized to acids, therefore compound C is an aldehyde. Why is it not a ketone? Because ketones cannot be oxidized any further. Now, aldehydes and ketones react with NaCN, HCN, and KCN to make a nitrile as a product. Why? Because all of these three have cyanide ion as the common ion. So, any aldehyde or a ketone will react with, let's say, HCN to give you COH and a cyanide ion. The reagent are HCN aqueous plus either NaCN, which is also aqueous, or you can use KCN, which is also aqueous. And the condition is that you heat under reflux. Now, let's say I have this aldehyde right here, and I'm told to make a carboxylic acid from this aldehyde. And there are two ways that I can make the carboxylic acid. First is the normal oxidation, where the R group remains as it is, but the hydrogen gains an O, so I get a carboxylic acid. But there is another way of making carboxylic acids from aldehydes, and that was the previous reaction which I explained. So you take an aldehyde, you react it with HCN plus either of KCN or NaCN, and all of them should be aqueous, and the product that I get is the double bond breaks into an alcohol, the H remains where it is, but I get a cyanide ion. And this is a secondary alcohol, because I have two R groups, because I have two bonds with carbon atoms. So this is secondary alcohol, not primary. And I have this cyanide ion. Now this cyanide ion, if you remember, I told you guys earlier that cyanide ions can hydrolyze into carboxylic acids. So this compound right here will oxidize to carboxylic acid. So this cyanide ion oxidizes to carboxylic acid, and the reagents were dilute HCl. Now comes the last reaction involving carbonyls, which is the iodoform test, and the reagents for this test is iodine and NaOH. Both of these should be aqueous. Now the compounds that give positive test for iodoform is, number one is ketones. So ketones which have a CH3 group at the end. The main condition for iodoform test is you must have a CH3 at the end, so a terminal CH3. So ketones reacts with iodoform, and what you get is the CH3 breaks off and you get C double bond O. The R group remains where it is, and instead of the CH3 you have an alcohol now, plus the CH will combine with iodine to make CHI3. And you don't need to know anything else other than the fact that since NaOH is present, the alcohol can become NaO, and that CHI3 is a yellow PP. Other than that, aldehydes that have a CH3 C double bond O will also give positive for iodoform test, and similarly the CH3 breaks off and what you get is CHI3 plus the compound as it is with OH replacing the CH3. Now finally, alcohols will also show positive for iodoforms, but not all alcohols. Only the alcohols which have this group present. So CH3COH would give an positive for iodoform, which means only ethanol can show positive for iodoforms, because when I add another group, it would not react. Only and only alcohols that have terminal CH3 will react with ethanol. So now we move on to the last reaction, that is esterification. Esterification is when carboxylic acids react with alcohols and you get an ester. Let's say I have methanoic acid and it reacts with ethanol. What I get is this ester right here, and the OH from the carboxylic acid and the H from the alcohol is removed, and these two combine together to give you the byproduct water. So you also get water as one of the products. So this reaction can also be said to be condensation. Now, how do you name esters? Well, you always start with the alcohol first. So the alcohol chain consists of two carbons, therefore eth. So I write eth, and next to the alcohol name I'll write YL. So then comes the carboxylic acid name. First I write the alcohol name, then I write YL, and then I write the carboxylic acid name, which is methanoic. So I write meth N. So I write it till N, and then I simply write O8. So ethyl methanoate. First I write alcohol, then I write YL, then I write the carboxylic acid name, and then I end it with writing O8E. Now this reaction is reversible. So esters will react with water to give you alcohol and the carboxylic acid back. So in this case the ester was ethyl methanoate, so the alcohol would be ethanol. Since the acid part has meth in it, I'd get methanoic acid. Now this reaction is known as hydrolysis because you're adding water instead of giving water. Now the reagent for this reaction is any acid or alkaline solution. But remember that acid hydrolysis takes a lot of time, and alkaline solutions take less time to hydrolyze esters, because the OH minus ion from the alkaline solution is a stronger nucleophile than water, and it doesn't reach equilibrium but goes to completion. So the double bond would split where I have the C double bond O and O. So this bond right here, C double bond O and O, will split, and the acid part, which is C double bond O, will gain OH right here, and the alcohol part will gain 1H right here to give you alcohol and acid respectively. And that pretty much is everything you need to know for AS organic.